Okay, here I want to finish up chapter 4 with a discussion of power and efficiency. So I want to just introduce what power is and then talk about a couple of examples where we compute power based on given motion or other assumptions. All right. So to lift an object against gravity, for example, to change its potential energy takes a certain amount of energy. Um, but it takes different amounts of power to lift it at different speeds. So if I lift something very fast, I have to supply that energy quickly, and that's a relatively high power. If I lift it slowly, I provide the same energy but over a longer period of time, so I need less power. So power is just the rate at which I supply energy or produce energy, and that's what we're going to discuss as we go through these slides. All right. So the power developed by a given force can be derived from the work. So if I take a given force F and apply that force to an object that moves through some differential displacement dr, that does a differential amount of work du. The time rate of the time over which I do that work will tell me the power. So the power can is the differential work divided by the differential time, or du dt. So power is the time rate of change of the work done on an object. So we can describe it if we replace du with f dot dr. P is f dot dr divided by dt, or f dotted with dr dt, but dr dt is the velocity. So power is force dotted with velocity. The dimensions are force times length over time. I usually think of it as energy per time. The SI unit is a watt, which is a joule per second, and a joule is a Newton meter. So a watt is a Newton meter per second, joule per second, however you want to look at it. In US, we usually use horsepower. One house horsepower is 550 foot-pounds per second. So foot-pounds per second is a common power unit, but also horsepower. 1 horsepower is about 750 watts. Now as we discuss power, we often talk about efficiency. So we provide a certain amount of power, say, to something we're lifting. But if there's some losses, then the actual observed power as we lift this object is not the same as what we put in. So the efficiency is a measure of what we get as output power relative to what we get as input power. So it's less than 1 by definition and is positive. So a couple of examples. First of all, we did this catapult problem with a FA-18 Hornet a few lectures ago, and so we're going to look at the power it takes to launch these planes with these catapults. So we have a 50,000-pound Hornet taking off from a stationary ship. It goes from 0 to 165 miles per hour in 300 feet. It's assisted by a catapult, so you're using the jet engines plus the catapult to do it. The engines generate 22,000 pounds of thrust. If we ignore drag and things like that, then we figured out that the work done on the aircraft by the catapult was 3.227 times 10 to the 7 foot-pounds. So the question is, what's the power developed by the thrust generated by the engines at the beginning and end of takeoff? And then what's the average power supplied by the aircraft to the aircraft by the catapult? And we'll assume here that the takeoff takes about 2 seconds. So we're applying enough energy to get this thing from 0 to 165 miles per hour in a 2-second time period. So we denote state 1 to be the start of the takeoff and state 2 to be the end. So the time from 2 to 1 is 2 seconds. And then we compute the power we need and the force and the velocity. These are given. The average power is the total work done by the catapult divided by the time needed for takeoff, right? du dt essentially. So since the force and the velocity are in the same direction, then F dot V, which gives us power, is just the force times the velocity. Okay, so at initially the velocity is equal to zero, so the power developed initially is zero. But by the end, we're going 165 miles per hour, and so the thrust, force, and the velocity have to be such that we're applying 19,400 horsepower, right? We were given the velocity, we were given the force, we just multiply them together to get the horsepower, the power. Um, since we know the work done by the catapult, then the average power supplied by the catapult is the total work done divided by the time, which is 29,000 horsepower. So it provides more power than the thrusters. But note, this is just average. This is peak here. This is average. So the average here is actually about half of this. And so it's what, maybe a factor of three, the power provided by the catapult versus that provided by the thrusters. All right. So let's do one more example. Okay, we have an electric motor. It's got a rope wrapped around it. The rope goes over pulley A, over pulley B, and then is attached at A. And so as the motor winds up the rope, it moves this pulley up and lifts this crate. All right, the crate moves with some velocity, VC. All right, so we're told that the efficiency of the motor itself is 85%, and the crate is 400 kilograms. So uh, in startup, it's a little complicated, but once it gets started up and the crate starts moving at a constant velocity, we're told that the power into the motor is 15 kilowatts. The power to the crate then would be 85% of that. And what we want to know is we want to get a free body diagram for each of these and look at the velocity at which the crate is moving at this as we supply 15 kilowatts. So the plan is to use the input power and efficiency to calculate the output power of the motor, and that power goes to the crate. Okay, and so since the crate's moving at constant velocity, then we know its mass, we know its velocity, so the force that's acting on it is the tension in the cable, and we can work out um, how fast it's moving. All right. So we do a force balance on the crate. There's uh, two tensions. If T is a tension in the rope, there's two of those because of the design of this system. So we have 2T pulling up, weight pulling down, and that equals the mass times acceleration. But we're told it's moving at constant velocity, so the acceleration is zero. So that tells us what the tension is. The tension is half the weight of the crate. Okay, we can also look at the kinematics. We can call this LC and this LM, and we assume, if we cut this at some point, then we assume that doesn't stretch, so that's a constant. So 2LC plus LM is a constant, so we differentiate that. 2LC dot is minus LM dot, so twice the velocity of the crate is the velocity of a point on this rope, or the time rate of change of this. So we know that the tension is half the weight. We have the input power at 15 kilowatts. The output power is 85% of that, 12.75 kilowatts. And that's got to go into the crate. So P naught, which is the power going to the crate, is just the tension times LM dot, right? Focusing on this right here, which is mgVc, right? So we know the power, it's 12 kilowatts. We know the weight, and so we can calculate Vc. So the crate moves at 3.25 meters per second. Right? We can do this a second way. Okay, so we can look at the force balance on the crate. So before we focused on the rope on the input side. Now we can focus on the crate. So we have some force up and weight acting down. And again, AY is 0, so we know what this force is. Right? And that force is applied to the crate. The force is equal to the weight So the power output power of the motor is FH times the crate velocity, and we get 3.25 meters per second. So you can kind of do this either way. You can do it focusing on the motor side of the rope or on the crate itself, and either way you get the same speed, 3.25 meters per second. All right. If the motor were 100% efficient, we'd get a higher velocity, and that works out to be 3.82 meters. So that's kind of how power works. It's pretty straightforward.